So the idea with Newton-Raphson is that we have a point here and we're trying to estimate that point there, that root alpha, I'll call it. And the idea that Newton and Raphson came up with, I don't know whether they came up with it together or separately or whatever, but it's called Newton-Raphson, is that you draw a tangent to the graph at the original starting point, which is hopefully near the root. So if I draw a tangent to this curve, that's x0, go up, draw a tangent, oh, that's not a very good tangent line, there. Not the best tangent line in the world, but hopefully you get the idea. And then what you do is you find out where that crosses the x-axis, and then that's your new estimate, x1. Okay, then you repeat. So if I go to x1, I draw the tangent to the curve x1. Oh, my tangent's all over. Look, I've kind of cheated and moved it left. But anyway, there's x1. So there's the tangent line, and that's where it crosses the axis. So that is x2. And you just keep going, and the idea is that these tangent lines are going to start crossing closer and closer and closer to that value alpha, x3. I won't put any more on because it'll get a bit muddled, but that is the idea. This is the formula, and the proof of the formula is in the proof section of the course. And you might be asked to prove it. Right. Let's come back to when it doesn't work in a minute and have a go at this one here. So we've got this function 3 sine x plus 2 minus 4x, and we're trying to find the roots of it. Now, I have no idea what that looks like, but if 3 sine x plus 2 minus 4x is 0, then 3 sine x will equal 4x minus 2. And I do know what that looks like, and I do know what that looks like. So 3 sine x looks like this. It goes up as far as 3, and it goes down as far as minus 3. And 4x minus 2 goes through minus 2, and it's got a gradient of 4, and it goes through the x-axis at half. Now, it's really important that I have drawn this in radians. If you think about, well, there's two reasons why it has to be in radians. One, you could just think of it as a rule. I'm going to differentiate. The derivative of sine is only cos if you're in radians. So that's one thing. The other thing is, look, I'm trying to find integers between which a root lies. Integer values of degrees. Imagine like 57 degrees, 58 degrees. That is the tiniest little, it's like that. Whereas this is 3 radians, more or less. So here's 1 radian, here's 2 radians. Sorry, there's 1, there's 2. It's a huge difference. So it makes sense that I can find a root between 2 integer values of radians, not really between integer values of degrees, like that. Right, so this is going to be pi, and this is pi by 2, which is about 1.57. And so a half is going to be about there, and it's going to go like that. It's not the straightest line in the world, but just pretend it is. So this point here is where that crosses that. And therefore this point here, this x value, that's a half. That, I'm going to call it alpha, is the root of that equation. So 3 sine alpha, that number there, plus 2 minus 4 alpha will equal 0. That's the root of that. So now we're trying to find the integer values between which it lies. So let's try, well, I can see, can't I? Where's 1? I don't know where 1 is, but 0 is there. And I could try 2. So when x is 0, what do we get? 3 sine 0 plus 2 minus 4 lots of 0, which is 2. What about when x is 2? 3 sine 2 with the calculator in radians plus 2 minus 4 lots of 2 is minus 3.27 according to the notes which I wrote earlier, which is negative. So there is a change of sign between here and here, and therefore there is a root of the function between here and here. So remember your full sentence for change of sign. F of x is this function here, is continuous and changes sign on the interval 0, 2. So there is a root in this interval. Okay, so it's somewhere between 0 and 2. Using the smaller of the two integers, which is 0, apply the Newton-Raphson formula. Now the Newton-Raphson formula is, let's write it down, it's an iterative formula. So every time you generate one, you stick it back in to get the next one. The derivative is on the bottom, so I am going to need the derivative. So in this case, xn plus 1 is equal to xn. That's your preceding guess, like the preceding one in the sequence of guesses. And then the function on the top and its derivative on the bottom. And the examiner wants to see this derivative, so make sure you write it down. Right, now I recommend that when you do the very, very first one, you show your working, but then after that you don't need to show your working. So if x0 is 0, then x1 is 0 minus, and then just make it really clear that you are putting that first guess, that first approximation, into the correct thing. Then you can write down what it is. Oh, it's 2. And then after that, you can just use your calculator. And you get all of these things. Blah, blah, blah. 199. And then you can keep going if you want. I mean, we weren't told how far to go, but we are told that we want 3dp to be the same. So far these keep changing. But then after this, once you get to about x5, then the first 3 decimal places stop changing. Oops, I've lost a 1. There we go. Right, so I think I now know what this is, but I need to confirm using a sign change. I think it's 1.199. So that means it's not the next one up or the next one up. So I want to show that it's between here and here. That's what I want to show. This is 1.1995. This is 1.1985. And the idea is that if I can find a change of sign on that interval, the change of sign of the original function, then the root will be on that interval, and everything on that interval is 1.1993 decimal places, which means that I was right. So, actually, do you know what? I'm going to get rid of this because it's not the easiest thing to check and I need the room for my sentence. So make it really clear what you're doing. F of 1.1985 equals, show the substitution in. Where's the function? There. This is what students do not want to do this. They want to just write down what the calculator says, but I'm telling you, you're more likely to get the marks if you actually write down what you're doing. So this is 4.8 for at least 3 significant figures, please. And then f of 1.1995, again, show me what you're doing with it. Don't just write down a number off the calculator. I want to be able to give you the marks, but I can't if you don't tell me what you're doing and then something goes wrong. This is minus 2.43, according to me. This one is positive, this one is negative, and I haven't got room to write it in here, but we would do the sentence again. The change of sign sentence. Right, finally, when doesn't it work? There are 4 different times when it doesn't work. Firstly, can't differentiate the function. It's a function that you don't know how to differentiate. That's a legitimate reason why it wouldn't work. Next, x0 is far, far from the root. If x0 is really far from alpha, then what happens is when you create the tangent at that point, you end up miles away and then the sequence might diverge. Okay, what else? These are the big ones. The tangent is horizontal at your starting point. So say, for example, my original one, the tangent is flat. Well, I'm never going to cross the x-axis. So I'm never going to cross the x-axis, then I can't find out where I cross the x-axis, can I? Because I don't cross the x-axis. So if the tangent is horizontal, i.e. the derivative at the starting point is 0, or close to 0, even close to 0. If it's close to 0, then your tangent will be like, whoop, and your tangent, even though we started really close to alpha, so it's not this situation, we're going to go miles away before we hit the x-axis, and the curve could be doing something totally different over there. Then, so if the tangent is horizontal, you can't do it. Tangent either doesn't cross the x-axis or crosses too far away. And then we end up in this situation.